Well, hi students. We're looking at section 12.9 today, and we're talking about curvature. Curvature is the rate at which our vector is changing direction, and we're going to define curvature as being the derivative of that unit vector with respect to the arc length, and where S is denoting the arc length and capital T being our unit vector. For our formula for curvature, it is being defined as the magnitude of the derivative of that unit vector divided by the magnitude of the derivative of that position vector. So what we're going to do, and now remember, curvature is the rate at which our curve is changing direction. So in example 1, we are to prove that lines have zero curvature. So what's up first for us is just to plug into our formula. So what we're going to need to do is get we're going to need to get our unit vector. So I'm going to take the derivative of our position vector and get that magnitude and write that down for you. So I've completed that. Now what I'm going to do is take this unit tangent vector and compute what we have, see what the unit tangent vector looks like. So what I have here is a vector on top, this ABC, from where I took the derivative, and in the denominator I'm going to have this constant, this a squared plus b squared plus c squared. Note that the derivative of my unit vector, how is this unit vector changing in time? The derivative of this unit vector, because this is a constant, equals 0, which then means that the curvature is also equal to 0. So my curvature would be this, the magnitude here would be 0 over this a squared plus b squared plus c squared. So if the curvature, how the line, how that curve is changing, the direction, how it's changing in time is equal to 0, we have proven that the curvature equals 0. On to the next one. For our next problem, I just kind of carried on with what we were doing before. They're wanting me to show what the curvature equals. So I did just as I did in the first one. I found the derivative of that position vector and then the magnitude of that position vector and found that to be r. Next, what I'll be doing is looking at that unit vector and how that unit vector changes in time. So we'll get that so that we can then get this curvature right here. So I'll go ahead and write that stuff down. Alright, so I got that unit vector, and then I found the derivative of that unit vector. How is that changing with time? And next I'll use my curvature formula. So this is 1 over, and this velocity vector is just this derivative of my position vector, so that would be an r. Next I need the magnitude of my derivative of my tangent vector, so I'll get the magnitude of that guy right there. So that is going to be the square root of, and that would be, negative cosine t quantity squared plus negative sine t quantity squared, after which I'll get this curvature is 1 over r. Note that I will then have cosine squared plus sine squared, which is the identity. Oh, that was all I needed to prove. And we're done with that one. There is an alternative formula for curvature, and it involves the cross product of your velocity and your acceleration vectors. So I will take my position and take the derivative to get my velocity vector, take the derivative of that to get my acceleration vector, and then I'm going to find their cross product and plug it into this formula. So I'll go ahead and get some of that computation complete. Alright, and remembering how I take my cross product, that is going to be, I'm going to find the determinant of those things that are not in the row and column with my I component and work my J and then my K component. I'll do that. Plugging now into my curvature formula, I need to find the magnitude of this velocity crossed with the acceleration vector. The magnitude of that would just be this 2a squared and square root, so that would end up being a 2a. And then I need the magnitude of your velocity vector quantity cubed, and that is going to be, I'm going to have the square root of 1 plus, and then I'll take that 2a quantity squared, and then I need to cube this whole thing, so I'll make that a little prettier. Alright, not much I can do with it, but there it is right there. And stunning as it may be, it is a little messy. For our next problem, we're supposed to find the curvature of a helix, so we're looking for K again. We're going to use this alternative definition, doing exactly what I did before, finding that velocity vector, that acceleration vector, and then I will find the cross product, which I've done here. The next thing I need to do after finding that cross product is I'll need to find the magnitude of that cross product. Well, I'll just kind of do that here because it might be a little messy, and then I'll try to plug it into the formula. Alright, a little messy, but I got the magnitude of that cross product. Now I'm going to need the magnitude of that velocity vector, and I'll plug that in, and once I get that, I'll just be able to use this curvature formula and get the curvature of this helix. With that now completed, I can just say that the curvature is the magnitude of that cross product, a square root a squared plus b squared, all over the magnitude of the velocity vector, a squared plus b squared, quantity cubed. Doing this computation, you will end up with a beautiful little a over a squared plus b squared. Nice. That one was pretty. Next up, we're looking at the principal unit normal vector, and in order to find that quantity, I'm going to need to know my unit vector. So what I'll do is I had to use what I did before, my definition of this unit vector, and I needed the velocity vector and the magnitude of that, and plug those in. The next thing I'm going to need in order to get this principal unit normal vector is I'm going to need to take the derivative of my unit tangent vector t, and then find its magnitude. So since I have these quantities now and they're very similar to what we've been doing, I'll go ahead and get the derivative of that unit tangent vector. Alright, with that complete, I'm now able to find this principal unit normal vector using the general formula. I just need this quantity here, that unit tangent vector, which is going to be this messy thing. I'll go ahead and pause you. And this principal unit normal vector, if you will notice, these guys drop, and then I can just run the 1 over a through, and I get minus cosine t minus sine t, 0. Nice. Everything fell out nicely, didn't it? Now we spoke of the principal normal vector and the principal tangent vector in terms of velocity, so now of course we're going to talk about those components in terms of acceleration. So very similarly speaking, we have formulas for those. We're going to need a few things in order to get this acceleration vector, and we are going to need, of course, the derivative of our position vector and that magnitude as well. So once we have that, then we're going to use the fact that in example 2 we found that the curvature for this circular trajectory was 1 over r. To get the tangential component for my acceleration, I'm going to need to take the derivative of that arc length with respect to time. And if you remember from our definition, this is just the magnitude of our velocity vector. And since our velocity vector is a constant, then that means this is just going to be equal to 0. And if the first derivative is 0, the second derivative is 0. So that tangential component, that a sub t, is going to be equal to 0 as well. So in just getting my acceleration vector, I'm going to look at it as this k, which is my curvature, times the magnitude of my velocity squared, which is then times this normal vector, plus the second derivative of my curvature with respect to time by this tangential. This is 0, leaving me with 1 over r times r w omega quantity squared times this normal vector. So our vector then ends up being r omega squared times the normal vector. And that would be the different components of the acceleration vector on this circular path. Alright, we would like to find both the tangential and normal components of acceleration. So first up, I need to get the velocity component and the velocity vector and then the acceleration vector. Now we would like to express this in terms of the tangential and normal components. So first thing I'm going to need to do is I'll get the tangential unit vector, which is going to be that velocity vector divided by the magnitude of that velocity vector. So I'll go ahead and compute that. So I have this unit tangent vector. Now in order to get this unit normal vector, I'm going to have to take the derivative of my tangent vector and divide it by the magnitude of that. So I'll go ahead and get that computation started. After a little bit of computation, then I took the derivative of my unit tangent vector, and then I found the magnitude of that unit tangent vector. Then in order to find that normal vector, I took the derivative over that magnitude, and with a little algebraic manipulation, quite a bit of messy stuff, I got this right here. Alright, so now I'm going to put all of that together for my acceleration vector in terms of both the normal and the tangent. The dot product being the easiest, of course, is my favorite. Just take your individual components, multiply and add. So I'll get a 2 here because I have 0 plus the 2, another 0 plus the 2 times 2t is 4t. So now I have each of the individual components. Now I'm just going to put that together to get my acceleration vector. Alright, now these are the components they wanted me to find. If I were to put that together, what I would end up with if I multiplied these out, I should end up with, if I did it all right after all of that, I should end up with that 0, 2 vector, which is what I had the very second step at the beginning of this particular problem. This unit binormal vector is needed to describe how these curves change in 3 space. So we're going to be not only talking about how the motion changes and the direction changes, but also in this 3 space how it's changing along this what we call an oscillating plane. So if I were to, without doing any calculations, find the unit binormal vectors, this would be 0 in that because the circle itself is lying only in that xy plane, that all those points are in the circle, and both the tangential and normal vectors are in the xy planes. So anything that's in that cross product of a tangential and normal vector would be equal to 0. Next, what we're going to do is just verify by doing these cross products that we are going to get 0 for a cross product. Now from example 2 and quite a bit of calculation, we found what the unit tangential vector and what the unit normal vector looks like. We're going to do that cross product. Note that the I component and the J component will both be 0 because anytime I'm going to cross it with this 0, 0, on that k component. The only thing we're going to have is something on that k component, which would then be crossing this. That would be a sine squared t plus cosine squared t. That's going to end up being a 1 for that k component, so this cross product just equals that k. Therefore, the torsion of this is 0. And that follows from what we got from A when we determined that this B vector here with the torsion, when we took that derivative, was 0, and from that right-hand rule we found that that vector B would be just straight in that k direction. Next, we're going to find the torsion of a helix, which means we're going to have to find the unit binormal vector, and then we'll go into finding the torsion for that. Now, first up, I'll have to find that unit tangential vector and unit normal vector, which I did in example 5, so I'm just going to write those down, and then I'll do the cross product to get that B. Okay, after a bit of computation, this is what we get for our unit binormal vector. Now, I'm going to need to find the derivative of this vector with respect to s. What I'll do, because this b vector is in terms of t, is I will just compute this and then over ds over dt and divide it by that. Now, the derivative of ds over the derivative of this arc length with respect to t is just going to be the magnitude of the velocity vector. So I'm going to need to get the magnitude of this r prime of t. And that way all I'll have to do is just find the derivative of this, the magnitude of this bad boy, which I can get from right there, and I'll do that up here at the top. So I got the magnitude of that velocity vector. I'm going to plug that in here, and you'll notice that since it's just the square root of this a squared plus b squared, when I plug it in here, you'll multiply these two, and what I'll get is just b cosine t minus b sine t, 0 over, when those two multiply together, they just become a squared plus b squared. Now, the last thing I have to do is take this derivative, which I just found, and multiply it, or do the dot product of the normal vector. So I'll get some more room and write that down. Alright, just writing that down and computing the dot product, I'll factor out that b, and then I'll have cosine squared plus sine squared, which is 1, and I will get that the torsion here is just b over a squared plus b squared. And that is a beautiful thing. Last, what we've got to look at is a summary of these formulas for curves in space. This is a nice little summary. I think I would have this sitting beside me when I went to take a test, along with examples of how to find each and every one of these. Alright, good luck, and if you need any help with anything, see me at the Collaborate. Thank you.